Yes, either it's Lebraise or Gurian, something like that. Sydney Longley, Daniel Markowski, Bozen Kiao, Edward Rankin, Ted, you Ted?
Yep.
Yep. Owen Sanborn, Colin Shanks, Matthew Thompson, to go by Matthew or Matt, whatever works. I do that too. I tell somebody say Mike, and then they say Michael, and it's like they don't remember. But anyway, Jordan, Jack Walter, Rayanne Warren, Alex Westcott, and Zach Wise Copeland. Is there anybody else? That's it? Oh, yes. What's your name?
Jeremy Severson.
And we can talk afterwards if you need to add form to the class. Or did you already join?
Yeah.
Okay,
I
okay.
signed up this entire time, I think.
Okay, I'll just double check that what's in my Jeremy Severson. Right, no, you are there. I'm sorry, I just must have skipped your name. You are on the list, so. Right. But good. So the forms, the information forms, I'll collect at the end. You know, they give you more information about who you are. You know, math background, computing background, interests. Within probability, it's used for a lot of things. So I can adapt some of the examples over the course of the semester to match some, you know, primary interests, or if I have that in the back of my mind as I'm looking through textbooks or thinking about examples, or stuff comes up in the news, and I notice something that matches some interests or is relevant, we can pull it into the class and work it into an example or something. So it helps me get to know you a little bit better and tailor the class to, you know, interests and an appropriate level. So for the class, there are a lot of different majors in this class. You know, math, computer science, but also you know, biology, sociology, economics. So I'm glad you're all here. It's probability and statistics. Probability gets used in a lot of different areas. So I hope you enjoy the class and find some relevance for the different fields that you're coming from. We'll try to get set up a solid basis in a number of different aspects of probability, so that if you would go on to courses in statistics or more in probability, modeling, simulation, that you would have a strong foundation to go forward. A lot of the course information, so we're going to talk about course information today and then get into some, you know, beginning parts of talking about probability. All right, a lot of the information for the course will be delivered on campus. There's you know, the syllabus, a couple of handouts today in terms of where we're going to be in the course and some policy and things like that. Dates that homeworks are due, dates for exams will be there. Assignments will be posted under a tab. The first one's actually posted. It's the same questions whether it's in PDF or Word. The homework on the due date, you'll write it on paper and bring that paper in and give it to me. I'll grade them, and with the paper I can more easily write comments, point out you know, assumptions or details, and then give it back to you. You could either type it if you like to type assignments, or write it neatly, but you know, just put your name on it, make it clear, and that will be good. You can work together to talk about, to learn the material, to check out understanding of problems, but everybody should write their own solutions. You should write it in your own words. Make sure that you understand the aspects of what you're doing there. But the main purpose is to learn the material, and so some help from your peers and office hours is, you know, can be an important part of doing that. Eventually I'll post solutions there, things. Under this files tab, there's some a part for lecture notes, kind of split it up so it doesn't look too much. So right now this one is empty. It's only the introductory material that is up. But eventually, some classes there will be extra handouts and things. Some of them will be printed, and I'll hand those out. If it's a longer document or just one picture, I might put it up there and then show it to you in class. But so anyway, the things that I do in class, I'll try to put up there. Also, when I use that smartboard, right? If I write things, and a lot of times I'll be writing formulas or going through examples, that can be saved, and I'll post those notes back under this file system, right? So if you happen to miss it, and we have Tegrity that's supposed to be recording for the class. So if for some reason you have to miss a class, whether it's sports or religious holiday or family or job interview or a field trip for another class or something, you can get the material and stay up with the class. This class, we want to go through a lot of material, but not just for the sake of going through material, but understanding it. So the class will keep moving along. A good way to stay to do well in this class is to stay up with it. Do the homeworks, do the readings. If things are confusing, ask about them in class, come to office hours, and stay up with things. If you have one of these days that you're sick or away for some reason, try to let me know in advance. Usually we can arrange something so you can still get credit for the work during that period of time, whether it's handing it in or an occasional extension here or there. But if you're staying on top of the work, doing the assignments, staying in communication with me, it's easier to work these things out. Yeah, but a lot of things will be there. In terms of the syllabus, the class schedule, you have a copy there. It has, I tried to do fairly detailed list of where we would be in the book. Often we're covering 1, 2, or maybe 3 or parts of a couple different sections in the book. So if you stay up with those in terms of at least maybe looking through them ahead of class, reading parts of it, after class, looking at those sections. I'll try to have the homeworks posted a little bit in advance. So if you look at the homework assignments, you can kind of start to see how it is going to connect to the material in class and there. Homework assignments are generally due on Tuesdays. We take some review time for exams and so on in there. There is a project at the end where you get to apply concepts in probability to something of interest to you. Right? It could be you have a data set and you want to see, does that data set look like a probability model, or what would be some summaries of it. You could do simulations. You could look at probability and chance as applied to statistical methods or in some area that you're interested in. But we'll talk more about that. There's a number of ways that can go, but probability and statistics for me is often in a context with some application where you're trying to learn something. And probability helps you reason and think about decisions and uncertainty that's occurring in the things that you're measuring. So there's a number of ways that project could go. We'll talk more about it when it gets to that time. There's a chance for you to try and write and investigate a little bit more independently and put into words some of the things that are going on, so that this class is not just formulas and kind of abstract examples, but connects to something in a more concrete way. So that's there. In terms of the thing that's called the syllabus here that has more of the course policies. I've listed here some. My office is in 259 over in John Marie. I'm in most mornings and some after class. So what I've done is picked the time periods that are best for me for office hours that also work with my other classes that I teach on Monday, Wednesday, Friday. And so these are kind of initial office hours, and we'll see how they go. If you can't make some of those office hours or have other questions or want to meet other times, it's fine to email me and say, look, my schedule is full at these times. Do you have another time to meet as the homework is going along. If there's particular problems or examples from class or other things from the book that you want to talk about, you can email and we'll arrange some time to meet. After a couple weeks, once everything's kind of settled down, we might take an assessment if we need to set another office hour at a slightly different time to accommodate schedules. This year we're using this book by Dick Schaefer and Linda Young. That's been around for a while. I like it as a book because it has a number of problems at increasing levels, from more elementary ones to medium to some more complex ones, and covers the range of topics that I would imagine seeing in a statistics book. There are a couple online resources that are free that gives other presentations. You could actually download these two things as PDFs. I might reference those once in a while, but there's no need necessarily to do anything with them. If you're in engineering and sciences, the National Institute of Standards and Technology has actually a handbook of probability and statistics. Not so much a textbook, but it has sections on probability distributions and simulation and case studies, particularly in engineering and sciences. And it's available as long as the government isn't shut down. So once that comes up, we might draw a few examples from those things. So in this class for computing, we'll use what's called the R statistical program or package. And so R is free. Over the last 20, 30 years, AT&T Bell Labs way back in the 80s had a program called S that was a graphical interface for doing statistics and data summary and simulation. And that became a commercial, very expensive commercial product. And then the statistical community created this thing called R, which is, I don't know why they chose R exactly as the letter, but as just it's free. It can be downloaded onto your own laptops or home computers. It's available on the network here at St. Michael's. It's very flexible. It has a lot of built-in functions for calculating probabilities from different distributions. It has a bunch of simulation tools built into it. It can do things, as you get into higher math classes, it can do things with matrices and solving equations. So it's really kind of a neat tool. It can do all the statistical procedures we use for all the classes in statistics here at St. Michael's, from the statistics 120 up to 451, and then many actual, graduate, senior research topics at the end. And increasingly, it's being used. It's very popular, certainly in statistics, biostatistics, public health. But as you go out into the research world, it is getting to be on par with other standard software like SPSS or SAS. And it's mentioned usually along with data science, in areas of data science with something like Python and other programming languages. So it's just an extremely useful tool. It's very flexible, it's very powerful, and we'll take it step by step as we learn it and use it. Right? We can use it to describe data. If we generate data from a probability distribution, we can describe that data. We can use that to graph and study probability distributions to see how they compare. We can actually do program more complex scenarios that require several steps and simulate it to get some idea of how things are performing to look at probabilities. But we'll take it step by step, not on the first homework, maybe not the second, but soon after that there will be, we'll use it in class, and then you'll have to do a few exercises. At the end of the course, if you want to do a project, it could be a tool that's used for that. If you're getting into junior seminars or looking ahead to senior projects and you might have data, it might be a useful tool for those things. It's possible you would have it at a job or internship in different fields, and so it could be useful to get a little background. We're going to cover topics in probability. We'll use those in applied problems. We'll look at discrete random variables, continuous random variables. We'll figure out how transformations work, and that's where some of the mathematical content comes in, because there's derivatives and integrals there. So that's why a course in calculus is useful. And then at the end of probability are some limit theorems. They get into central limit theorems that are kind of the basis of making confidence intervals in statistics. So kind of the foundations that justifies the standard procedures people use really come out of the probability theory. There's some homeworks, project, a couple in-class exams, and a final. If you do the homework assignments and the reading and keep up with that, I'll give out some practice problems and we'll do some review days before the in-class exams. So if you can do pretty well on those, get a lot of points on those exams, by the time you get to the final on the project, you should be in a pretty solid position. Right? So if you stay up with the class and keep learning along the way, ask questions when you don't, when something's unclear or you're not sure how to do it, do something, then things can turn out pretty well. So if you drop off and miss parts and kind of aren't doing things in the class for a couple of weeks, you will be able to recover and catch up, but it's harder to do. That's probably true for most classes. But this, since it's built up on mathematical tools and probability, and it's kind of cumulative in that sense, it's good to keep up. If anybody has learning differences or learning disabilities, usually I get a message from the center in the library that suggests accommodations that can be made to make the class accessible to everyone in the class. If that pertains to you, probably I'll get a message. You're welcome to talk to me outside of class, or send me an email saying that just alerting me that I should be expecting something, and I found it very a useful system in past classes, and it's something that we can work with. In terms of religious holidays or other things that might take you away for 1 or 2 days for some reason, just try to stay in touch and stay up with the work, and let me know as soon as you know something like that is going to go on, and you probably can figure out some ways to keep you on track and help you, allow you to get the credit for the work that's going on during that period of time. So. But any questions about course mechanics, this type of stuff? If anything does come up, let me know, and we can. One. So thinking about probability and chance and randomness, right? Where do you think of what applications do you think about that involve probability? Maybe you look through the book, or maybe not, or maybe read the course description at least, and choosing this course. Does any particular topic area or have any type of interest come to your mind when you think about probability? Yeah.
Gambling?
Gambling, yes, right? So, yes, gambling was one of the historical origins of people thinking about probability and chance and trying to do it in a more formal way, right? So certainly that is there, whether it's betting on something, or the lottery, or games of cards. We'll use some examples from that, but we won't always be about that. In some of those games, there's simple rules and simple things to ask about, but solving it can illustrate using some techniques. But anything else?
Investments.
Investments, yeah. Right. Are things going up? What's the distribution? What's the likely trend? Forecasting. investing, right? There's something else that's kind of cool with investments, right? If you can get two investments that have a negative correlation to one another and can invest in them, there's ways you can set up portfolios of investments that on average do maybe not as well as if you had chosen the optimal one, but still do quite well, but have a much less variance. Right? They kind of trade off from one another. You can kind of trade off the risk for things to get what people do in Wall Street, we're getting a package of things that kind of offset each other, that if one goes up, the other one tends to go down, or if that one goes down, the other one goes up. And they do it in a certain way to make advantage of correlations. We'll look at formulas for correlations and linear combinations of variables that would be the types of things that people look for in investments. You know, anything else? So really it's wide open, right, in terms of that, right? So, you know, elections and polling. More generally, survey selection. One area I work in is survey statistics and survey sampling, and there's a probability of selecting somebody into the survey. And in large-scale surveys, the probabilities are usually not the same for everybody, right? If you want to estimate totals, like total sizes, I was involved in surveys when I was living in Iowa with the Department of Education, and we're doing surveys about students. Well, it's hard to directly go to the students. You usually go to the schools and then the students within those. So if you pick certain schools to go to, do you want to pick all the schools equally? Well, some of the schools in Iowa had 100 students. Some had, you know, well over 1,000. You know, same thing in Vermont, right? That there are some schools, some high schools that are, you know, quite, you know, decent in size, you know, between 1 and 2 and 1,000. There's other high schools that are closing because they're so tiny, right? And so if you wanted to represent all students by picking a few high schools and then interviewing students, you probably wouldn't want to pick all the high schools equally. Right? If you want to cover the totality of the students pretty well, you need to put more probability on those big schools. So it's used in design that. You know, elections and polling. Right, probabilities are essentially estimated very often in medicine. What's the probability somebody is going to get better from a disease after some treatment? So medicine, probability of successful treatment. Personalized medicine. Is a branch of medicine that looks at predicting which of many therapies would be right for you, right, based on your personal condition. Right? So it's a conditional probability. Given that you are a certain gender or an age, you have certain health indicators, maybe some genetics and family history, what should we do for you to help you improve, right? So there's this estimation of probabilities at that level that's really of use. Besides investments, right, there's kind of related to that, there's just general economics, right, unemployment rate, employment rate, labor force participation, those type of things are also probabilities, right? There's a chance. In statistics, we try to estimate those things. Risk and insurance. Shirley uses a huge element of that is looking at the chances of an accident, of having to pay coverage for somebody, right? And all things like people's behavior, you know, are they smoking, drinking, their ages, their past history, all goes into a probability calculation of that. Right? So gambling, you know, certainly sports. Right? That's kind of related to gambling, but you know, you don't have to bet money on it to be interested in a team winning, and so on. Forecasting. Anything else weather, right, prediction, right, our probabilities and forecasting. So we could go on, right, and you can think about that. The first problem on the first assignment is to describe an area of interest that involves probability. So you could take one of these, or you could think of something totally different. You could look at the newspaper over the last few days. There's almost always something involving chance or uncertainty, and try to find a source, or it could be a newscast, something you hear on the radio. It could come from anywhere, but just describe something maybe based on your major or related to another course. And so it's not that formal in terms of what it's asking on that first one, but just to start thinking about how does probability enter the things that are going on in your life or the society around you, and do something with that. Just write a little bit. So to talk about probability, we're going to define some terms. Okay. So probability begins with some random phenomenon. Some random thing is going to happen. It could be something like rolling a die. A dice. A die. Single. Right? And then noting the outcome. Right? It's random. You don't know what's going to happen until you do it. In surveys, we could pick a person from a population, right? And then, for that person, we can, so the roll a die, we can record the value. And we could pick a person, we can record the employment status for that person. And as you're going out and doing the survey, each person, you're not going to know what their ultimate answers be until you ask them, so there's some uncertainty in there. Right. You could do surveys of just about anything. You could take a car, on the road, stop them, and ask, mileage. Right. Do other sorts of inspections for them, right? That you could randomly sample cars that are registered in Iowa and go find those cars and get information about them. And depending on which one you do at its current status, you're going to get different answers. And in more scientific applications, if you're running experiments to see how the bacteria respond to certain types of antibiotics, and if they're taken from different populations that might have done incomplete, uses of antibiotics, to see if there's any resistance there. So an experiment could be taking this a petri dish with the antibiotic, the bacteria growing in it, putting in the antibiotics, and then recording outcome in some way. Right? And often there's multiple ways to record any type of outcome. Is it successful or not, or what percent of the culture was eliminated by the treatment, or something like that. But it's random. We don't know what's going to happen until we actually do it, and that's where we begin, with something that's going to happen. We record some outcomes. Right? These are the different possible results, of this phenomenon, and it's going to depend on who we're asking, what kind of the unit of study is, and how we're asking the question, and how the random phenomenon is done. So say it's a six-sided die, and we're rolling a die. We can record the values. Right? So for the single die, you could have these numbers 1, 2, 3, 4, 5, and 6. In reality, the die will have little dots on it, and we know that you translate those into adding, but there's a measurement process that's even embodied in that. When you're doing things like picking a person and recording something about employment, that's actually a really complex question. There is, in the United States, the survey that determines the official employment levels is called the Current Population Survey. It's been going since the 1940s. and interviews about 72,000 households per month in the United States to estimate employment. And it just doesn't ask, are you employed or not? It's about 7 pages of questions. Right? Have you been looking for work? Have you been earning money for occasional jobs? Do you have a regular employment? And the status that they record is not just employed or not, but includes, are you active in the labor force? If you are, then are you employed? If you're either employed or unemployed. So for that employment one, so labor force, are they in the labor force or not? If they are, there's a measurement of employment. There's a measure of unemployment. According to certain standards. But the data that comes out of that random process is really quite a bit richer. Right? You get the number of hours somebody works, the number of times they work in a regular job versus other jobs, and there's myriads of details that might be taken out of that. So the outcomes in real applications can be quite complex. Once you're picking cars, mileage, the inspection has any number of things. It might be a measurement of the exhaust expressed in scientific units, right? The amount of carbon monoxide that's coming out, the amount of other pollutants that's coming out. And those are all the different type of outcomes that come out of there. Sometimes for a person, right, for instance, we wouldn't just have one single thing that we're measuring. You can take many of these examples and think of any number of things. Right? Instead of recording the die as 1, 2, 3, 4, 5, 6, you might do it as even or odd, and say, if it comes up 2, 4, 6, it's an even number, and 1, 3, 5 is the odd numbers. We might record that as the outcome. Depending on how we want to define it. Some rolls of the die might give you large values, others might give you small values. In the car testing, once you're inspecting, does it pass or not pass? Is it pass clearly? Is it in the kind of the gray zone where it's pretty close to the standard, maybe has to be retested or failed? Depending on how you set things up, you're going to get different outcomes. And we might want probabilities on all these different things. So so outcomes are the individual things that come out. Sometimes these outcomes, are expressed in different ways. So a set is just a collection of objects or things. In a set, usually written with little braces, like this, with everything in the middle, and the objects are put in there. Order doesn't matter for us. It's just a list. You could list it starting from the biggest, going to the smallest, or the smallest going to the biggest. It's still the same set of things. So for that die, the set has these different values here. And, 6-sided die, you could use other dice that have maybe 8 sides or 10 sides or 20 sides or something like that, right? So that would change the problem. If you're interviewing a person, there's a number of different sets that might describe possible things that we might measure, right? We might have a set related to age. So if we recorded age in years, we might just record age in years. If it's a survey of adults, we would think that our ages should start at 20 and go up to some upper limit. Sometimes when we list out a set, it's not all that clear sometimes what the upper limit would be. Many times it doesn't affect what we have. Sometimes the upper categories get so rare that they're going to have small probabilities. But if you wanted to list this, you could go listing forever, but you're never really going to get somebody that's more than 130, 140 years. Maybe that's in the future we'll have something that. If you don't want to interview anybody over 99, that old, or maybe everybody over the age of 100, you're just going to classify them as 99. They're in that upper, very elderly category. And you get these different sets. Other things are harder to say exactly what the set of things that would be, right? So let's say you're picking a car, or picking, I don't know, picking something. Let's say we're looking at trees, and we're sampling different leaves on the tree, and one thing we record about the health of the tree or the characteristics of the tree, could be the color, or maybe we're looking at, instead of sampling the leaves, maybe we're sampling maple trees. Maybe we're looking at the maple sap that comes out of these trees. And if you're taking randomly picking from the different trees and then recording what the sap comes out, you can record a number of things, right? So you might record the color. You might record, color. You might record sugar content, and other things of taste, right? The color, right? One concept often can get recorded in a number of ways, right? For the industry of maple syrup, they record it as amber or darker. They have a few different categories that they put them in, right? But within each category, really, if you want to get scientific about it in terms of measuring the different components of color, right? You could give quantitative measures for something that would be produced now. Right? So if you want to try to reproduce that color on a computer screen that would match this sample, right? They record the amount of red, green, and blue, or there's other ways of denoting color by different pigmentations and things like that. So it might be reported in categories. There might be more quantitative scientific things that record those categories. Sugar content, right? You might measure it in terms of a scientific amount of calories that are related to that. Concentration per liter or per ounce or cubic centimeter or something. That might be categorized into high, medium, and low, right? But we have a different idea of outcomes, right? And in probability, the sample space is going to be the set of all possible outcomes. So a sample space for probability is going to be the set of all possible outcomes. And as I'm trying to convey from some of these examples, describing that often depends on the context and exactly how you're measuring things, how you're going to record it, and it can be different in different contexts. But you want to think about the all possibilities that cover the range of things that can happen in your particular random phenomenon as you're deciding to measure things. A subset is then a set that is a group of just some of the objects that are there. Right? So a subset is, right, so a subset is a collection of, right, so part of a set containing some of the objects, or maybe none of the objects that are in there. And so an event in probability, say the sample space, is often depicted by just a letter S. An event, say A, often different events, different questions that we might ask. We're going to say it happens if event A happens, if such and such a thing happens. It's called A, B, C. Often books tend to use capital letters at the beginning of the alphabet, you can note these things, but there's really no restriction on that. An event A is a subset of the sample space. In terms of math notation, A is often written as a subset of S. And so by illustrating this, right, so you can think about some of these things, you know, so you roll, say, you know, a 6-sided die. If you're interested in asking what's the chance that somebody gets a 5 or 6, right, you can set up a subset, so the sample space of all the possibilities is all of these things. We can ask a question: what's the chance that somebody rolls a 5 or a 6? Maybe you're in the midst of a game and you need to get so far to get, you're playing Monopoly, and if you get 1, 2, 3, 4, you land on properties where people own things, you have to pay money, so you want to know what's the chance that I get a 5 or 6 to get far enough to jump over that bad territory. All right. So if we're interested in event A, that you roll a 5 or 6, right? So in set notation, it's 5 and 6, right? It's a subset of that. Basing on some constructs we'll do with probability. We'll talk about how would you assign a probability to that event. If all these events are, all the dice are equally likely, there's 2 out of 6, so it's just 1/3, and that would be the typical answer in this, but we'll think about that a little bit more. For this course, you can write things as A, you can write them as a statement, like roll a 5 or a 6, right? Or you can write it in set notation, right? All those things are fine. It clearly describes the event that you're interested in, the set of outcomes that are of your topic. And so what's the probability of A? What's the probability of rolling a 5 or 6? Or what's the probability of that set? It's all going to be the same. Right? So we do use math and math notation, and the book has a fair amount in there. But it's I like using ordinary words to describe events, because when you get out in the using probability and estimating outcomes and chances in the real world, to communicate with other people, you need to phrase it in terms of those topics. So another event could be something like roll 1, 2, or 3, a smaller number. Or you could have, say, the event E, that you get an even number. Sometimes it's convenient to change the symbol so that it matches up. Eventually we'll do 2 or more different events and how they're related to one another, and sometimes it's convenient to use letter symbols that match those things so they're easier to remember. In other cases, in terms of subsets, say we survey people, ask somebody, survey a person, and we're asking about everything to do with employment. What would be some subsets that we would be interested in terms of the response we might get to some of those questions about employment? Yes?
I have a full-time job.
Yeah, so full-time job, right? So not only are they employed, right, but number of hours. So what's full-time employment?
40 hours a week.
So right, so we could ask, number of hours employed. So we could be, that 40 or more hours per week in a job. Some places still count 35 hours a week as equivalent full-time employment, right? So kind of depends on the industry and the state and the federal program to whether they count it like that. Yeah, so 40 hours or more a week. Maybe underemployment is 15 or less or something, right? So even if people are getting jobs and are counted as employed, if working adults are not employed enough, maybe they're not making enough money to pay bills, and they're technically working, and that measure of unemployment looks low, but they might not be fully employed or fully, right? And so, yep, employed, are they in the labor force, right? About 30 or 40% of the adult population is not in the labor force, right? They're retired, they're caring for children or other people, they just don't have jobs. They're in transition between jobs. So a number of people are not in the labor force, they're not working, or they're not looking for work, right? Outside of the house or whatever they're doing. Yep, and so those different subsets can be of interest, right? We'll use these sets and these ideas of sets to set up a little bit of logic to work with things. Right? Disjoint, some events that we'll be interested in are called disjoint events. They're also called mutually exclusive, that they don't intersect in any way. So two events are disjoint. If they have no outcomes in common. So they're to be non-overlapping. Another way of saying this, they don't overlap in any way in terms of the outcomes that are contained in there, right? So things like employed and unemployed status are disjoint. The rolling the dice, rolling even and odd numbers, right, are disjoint. If you randomly pick somebody, ask them their age, often some things get summarized by age group, right? So if you get less than 35, 35 to 55 or 65, and then over 65, right, you get these distinct age groups. Often, let's see, instead of doing we'll do a few events on those. So let's define something in terms of probability. So kind of an elementary idea about probability is that we have our sample space. So this is all of our possible outcomes, everything that we might happen. And A is going to be some subset of that. It might be proper subset, or you can think about it. It could be the entire thing itself. It works whether it's actually smaller or everything. Yes.
Is that a less than or equal to sign, or is it like a C over?
This is a little thing that means subset. A is a subset of S. Right? Here's what this little thing means. Sometimes, right? And so that little extra equal means there could mean the whole thing. We could be what's the probability of the entire thing. Often we're interested in something that's smaller, right, in there. But that is just saying, so A is an event, some collection of our possible outcomes that we're interested in for some reason. Information regarding height, what's the chance that somebody's over 6 foot tall? And so A might be that special category that somebody's over 6 feet tall, and S would be the all possible heights that we might measure. And then probability is given by what's called an operator P that's going to assign numbers between 0 and 1 to the different events that we have. So it's going to have certain rules that the probability of the entire space is going to be 1. if S contains all of our possible outcomes, the probability that we get something in that space has to be 1. Right? And then the probability that's assigned to some set is going to be between 0 and 1. Right, so, and these represent the chances that it's going to happen. As the random event happens, and we measure whatever we're going to measure, right? And if the outcome that comes is in that set A, then it has occurred. And the chance that A has occurred, chance or probability that A occurs in one trial of our random phenomenon, right, then we're going to call that the probability. Right? One thing we'll do in this course as we go forward is think about how do we get those probabilities? How do we actually quantify things for different cases? An initial one we will have is when the different outcomes are equally likely. Like when you're rolling a 6-sided die, the probability that you get an even number, that you get 2, 4, or 6, if there's 3 outcomes and they're all equally likely, 3 outcomes that are even, out of the 6, there's half of them. And so if they actually occur with the chances that are proportional to those numbers, then the probability is 1/2. Right? So, yeah. So we assign these probabilities to these things, and these are going to be outcomes. Sometimes these are going to come from kind of the description of the physical experiment. Sometimes they're going to come from things where we count the number of outcomes that are consistent with an event and talk about whether they're equally likely. And other times it's just going to come from other sources, right? It might come from survey data or just hypothetical descriptions of what we think the chances are, right? Sometimes they come from models. But the source of these probabilities and thinking about them is something that we'll look at throughout the entire course. Different binomial, normal, different other probability models for describing things, and the chances and how they relate to one another. So let's take 2 examples, right? So hypothetically, so let's say we're going to take an adult in the U.S. and ask them a question, and we're going to ask them whether they think Trump should fire the special investigator, the special investigator Mueller, right? That's investigating the links between the Trump campaign and Russia and other irregularities. Right? So that could be an event A. If they say yes to this, then that will have occurred. Right? Let's have a second event. We're going to ask you another question. Right? Trump should declare an emergency and build a wall. So if you ask them that question, that would be the second question, and that might either occur, they might either say yes or no to that, right? We could look at, let's imagine, just hypothetically, that the probability that A occurs, if somebody says yes to this, is 20%. And I'm just making these numbers up. I don't have a particular survey that's giving me these numbers, so we're just going to work with this. It might be high, it might be low, I don't know, right? So, and imagine that this is 30%. One thing you can think about as you see probabilities given as fractions, you might, or as decimals, you might think about turning them into percents. Right? So the probability is 0.2. Probabilities we want to be between 0 and 1, but that's 20%. So that if 20% of the people from the population would actually think that, have that opinion, that would be the probability. We randomly pick somebody, the chances we find somebody by randomly picking the whole population that they have that characteristic would be 20%, and 30% for that one. we can combine events. Right? So this little thing is called union. It also could be written A or B. So this would occur, this is going to be a new event created from these two. And it's going to be true if either A or B, or maybe both, it's inclusive, happens. A or B or both occurs. So in words, right, so this is either they think this or they think this. Trump should file a Mueller and stop that investigation, or he should declare emergency, or one of those things. Right? They could agree with one but not the other, or maybe both. Right? A intersection B is, in our book, we won't need to use this notation throughout the course, but in this beginning section it uses it, and it looks like it just writes AB, meaning that both things. This upside down one is called intersection. And in words, it might be A and B. It would be the event that they both happen. So this would occur if somebody answers yes to the first question and yes to the second question. That Trump should take both of these actions. I'm not getting into the politics of this. I'm not debating these things, right? But you might be interested in these things. Right? So are these two events, A and B, disjoint?
No.
No. Right. Somebody could say yes to both or no to both. Right? They could both occur or not. Right? They're not exclusionary to one another. Right? If B were that they should not fire Mueller in that investigation, and they're opposites of one another, then they would be. But these both things could happen, so they're certainly not mutually exclusive. What's the probability of A union B? What's the probability that at least one of these two things happens? Right? You want to think about that. Is the probability, could the probability of A union B, could it be the probability of A plus the probability of B? Which would be 0.2 plus 0.3, which would be 0.5. Is that true?
No.
Not necessarily, right? The people that say, well, why would it necessarily be true, right? This is probably too high in how I would think about the context of this problem in this case.
I guess if 20% of the population thinks one and 30% thinks the other, the odds that they overlap aren't 50%.
Yeah, there's probably some overlap between these two things. And so one way of depicting some of these programs, this kind of scenario, is something called a Venn diagram. There was somebody named John Venn, who was a mathematician back in the 1600s or so. And so if we draw a box, and that's our entire sample space out here of all our possible outcomes, kind of symbolically representing all the possible things that might happen when we ask these two questions. And then this circle is A, which means yes to the first question, right? And B means yes to the second question. We can put numbers in there that represent probability, right? And so there's certainly, the probability of A, we said, was 0.2. So all the area inside of A has to be 0.2. All the area inside of B has to be 0.3, but there's this overlap in the middle. Right? If they're not disjoint, then these things are not separated. And if you just add up everything in A and everything in B, there's a little bit of overcounting. Right? So what would we have to do to make a proper adjustment? Right? So the probability of A union B, and this is or, grouping them together, catching them in a cup or something, probability A plus probability of B. What if we double counted by adding all of A and all of B together?
The people who believe both.
Yeah, people who believe both. Where are the people who believe both?
In the middle section there?
Yeah, this one. This would be A occurs because it lands inside the circle of A, and B occurs because it lands inside the circle of B. So it's both, right? So we've counted it once for the A and once for B, right? So to make this really work out, we have to subtract that intersection, right? Where they're together. So it depends on what that is. And so if we think that's high, if we think that the people who favor of taking one action are the same people, you know, are also going to have that other one, you would think that would be pretty high. So let's say it's 17%. Let's say 17% of the people you pick are going to say yes to the first question and yes to the second question. So the probability that they say yes to either one is you have to subtract that part in there. So this is 0.5 minus the 0.7, and it's 33. So 33% say yes to at least one of the two questions. I believe that the overlap is fairly substantial, right, out of this. Then the chance that you get either one doesn't increase that much. What you can do with this, and I'll use color, right, is once you know this intersection part in here, you can put that in the middle. 17% are at that intersection there. So how many should be here? And what is that area represent?
0.2 minus 0.17.
Yeah, this calculation is going to be 0.2 minus 0.17 is going to be 0.03. So there's 3% there that are in A, but not in B. So the probability, so it's yes to A, but no to the B question, is just going to be 3%. And if you take all of these combinations, A by itself or A with B, and add those together, you get the 20%, which is the original statement. So what goes on that side? Kind of the same logic, right? But B had 30% overall, right? And if you subtract that, you get 0.13, or 13%. So this part that's outside of here is the probability of no to A, right? It's not included in A. So they're not saying that he should end that investigation, but they say, you know, build the wall, right? So they say yes to B. So that would be this 13%. So we should be able to calculate, right? We should get the same answer whether we do it this way, probability of A, probability of B, and minus the intersection, or we add up these three pieces separately, right? These three separate pieces are disjoint, right? If, you know, A but not B is distinct from yes to both, and that's distinct from yes to B but no to A, right? So those three parts can be added up, right? So, and if we take so the probability of A or B can be the probability of A but not B. This little line over the top is what the book means for the opposite or no, right? So some other books will use a little C for complement or opposite. Other books will use a little prime, meaning not C, or you could do not. I don't mean to be confusing by adding all these extra little terms in there, but if you look at other books, people might denote it other ways. I prefer saying it in words that B does not happen, that it's not B, or it means that they say no to question B, right? It's more plain language. But once you get into books that talk about that, they use slightly different things. If you keep in mind that you want the opposite of it, they use some notation for that. So this would be A, not B, and then there's A and B together, and then there's not A and B, right? So that was the three components of this picture, right? So if you add those up, right, the 0.03, the 17% overlap, and then the 13%, we should get the 33% as before. What percent would say no to both questions?
1 minus 0.23.
Yeah. So to get the opposite of things, right, we'll take 1 minus the probability. This whole probability of the entire sample space is 1. So there's 33% included here. So 67% or 2/3 would say no to both questions. Where'd that go? There it goes. Right. So this is not that complex of an example. Partly it illustrates the symbols that the book uses to describe some of this business. Right? But often in probability, there's more than one way to calculate some of these chances. Right? Sometimes breaking it down into pieces is good. Sometimes thinking about the overlap is a way to go. Some books some problems in the book, they don't give you A and B and the intersection. They might give you these 3 separate pieces, and then you have to reconstruct it. Or they might give you something out here that's not in one of those, and then 2 of them. There's kind of 4 areas, and as long as they give you 3 of them in some form, 3 numbers, you can subtract and work with it to get the others. And many things in times in probability, the probability of a, well, let me not write that here because we don't have much space, but taking the opposites are often useful, right? So the probability of A was the probability of yes to the first question. And that was 20%. So the probability of not A, or the probability of no to the first question, it's just 1 minus that, right? It's the opposite. 1 minus that, or 80% would say yes if 20% would say, or 20% would say no if 20% would say yes, or, right, the opposites. The thing that we did with no to both is no, right, so this is no to A. And I'll write the intersection to say that it's and, right? And no symbol here, no to question B. Well, we could do 1 minus the opposite of that. What's the opposite of saying no to A and no to B? That was saying yes to either one of them. Right? The opposite of that was A union B. So yes to either one. Or both. That's an inclusive or that we use in this. Right? And so the book points out that there's certain set operations. Right? That the opposite, have sets A union B together, the opposite of that entire thing, we're taking the opposite of this was that A does not happen and B does not happen. So this is a little bit of set notation. We won't need to do a lot of that kind of formal set notation for manipulating things. If you have seen some of this before, you might be able to, follow it through. Sometimes it's useful for reasoning out things that are a little bit more complex. Most of our problems that we have you can do mostly in terms of the words. Right? It won't be quite as complex. And I'm unlikely to ask a question, just go through and prove some set theory notation thing. But it does exist in the world of probability and people that look at mathematical aspects of probability. And essentially what we did by saying no to both is 1 minus the chance of yes to either one. And that's how we did that subtraction. So really it was doing, you could look at it as, well, first you do the set notation and then you calculate probabilities. But we just kind of did it along the way. So, but any questions about those things? Right? You can do more complex things with these Venn diagrams. So because we're Tuesday, Thursday, we go about 1.5 class periods, so we go to 11:50, right? So if you need a break during the time or get a drink of water or something, I understand at some point you need to get up. But feel free to ask questions too as we go along. Some things in this class, like counting and some of this stuff, you might have seen in some context before, but it's it kind of sets it as a basis for going forward. So let's look at a new example. Let's do a survey of students. Think about a survey of students, and we're going to ask about the technology that they have in their dorm rooms. So we're going to have, this might be phrased more in my generation than yours, right? So do they have a stereo player of some sort? B, do they have kind of a iPod or something like that for doing music? Everything now is kind of taken into the phone, and there's just kind of one thing. And maybe do they have some type of computer? So we can ask them different technology. You might be interested in asking about different things. Do they have a separate television? Do they have, at one point you might have asked, do they have a phone answering machine? Not that anybody has those anymore, right? But over time, surveys would have asked about technology in the classroom, right? What do people bring to school, right? How is it changing? Right? And if we have these 3 things, there's all sorts of statements that we can make about how they intersect and overlap to describe the population, right? So we can make a Venn diagram. Do this. This is all the possibilities, and there's I want to try to draw these big enough so there's space in the little intersections there to write numbers and so on. So this is A, and this is B, and this is C. And this one, you can write whatever is useful for you in terms of keeping track of things. So stereo, iPod, and computer. I did make computer C because that makes sense. It's helpful to remember that. But you can write whatever you want to keep track of those things. Right? And depending on a number of statements, you could actually fill in all of these things and answer more complex questions. Often news articles that report on surveys only give you part of the information. Right? They'll say how many have stereos, how many have iPods, how many have computers, how many have nothing. But they won't necessarily give you all the different categories. If you had the original survey data, you could figure that out. But let's say they said that 5% have all 3. How is that going to be represented on the graph? once you get multiple overlaps of more things, it's easier to start where they overlap in the middle. Right? So is it clear that 5% would be in the middle? That little place there, it's inside of A, it's inside of B, it's also inside of C. So that's the special place where they all three happen, right? So that student would have all three things. Right. Let's say that then they say 15% have a stereo and iPod. They seem to have two sources of music, right? Plus computer, of course, another thing. But they have that. So what would we want to add to the graph once we have that information?
Fill in the overlap of A and B.
And there's no overlap of A and B, right? Stereo is A, iPod is B. Do we want to put 15 in there? 0.15? No. So part of it is in the triple overlap, right? So of this, there's 10% left here, right? So this entire spot right here is the overlap of A and B. The probability of A intersection B is 0.15. The probability of A intersection B intersection C, right, is the 0.05. Sometimes A and B are together. C also happens, but sometimes A and B are together, but C does not happen. And that is how it would break out there. Is that clear from those two statements about? Let's say 20% have a computer and a stereo. Computer and stereo is going to be this one. Right, that's computer and stereo. Again, 5% is taken by the triple overlap, so that has to leave 15% outside of that, right? So that has to be 15% here. How about 10% have an iPod but no stereo and no computer? So 10% only an iPod. So in common language, there's more ways to say things than one, right? Only an iPod means they have an iPod but no stereo, no computer. So that's 10%. So where does that 10% go?
B. Both.
There's an iPod. So it's in B, right? So iPod is B, right? But there's 1, 2, 3, 4 areas that are in B. We have 2 of them filled in. Is this 10% redundant to anything, or is it different? It's iPod, but not the other one, right? So there has to be 10% over here. I'll put 2 lines under that one, and then put kind of 2 lines under this to try and make some correspondence. Right, so this one is iPod. Any of those is iPod, but it has no stereos and no computer, so those other circles are excluded. So it's just that. If stereo is 50%, probability of A, probability of stereo, 50%. So we fill in that's the last, that gives us enough information to fill in the last part of the stereo, the A. What value do you want to put in there? Yes? 20%, yeah, 20%, right? So that's at 20%. So what is this 20%? 20% have a stereo, but they don't have an iPod, or they don't have a computer. Right? That's the only thing that they brought with them. Right? If 60% have a computer, 6 or 60%. Let's see. Can we do? It doesn't quite tell us everything. Because there's two parts here. So we know that there's 40%. I think I need one more piece of information to make this work out. I'm going to say that 5% have none. Right. So I need a 0.05 out here. And so do iPod, 60% have a computer, so 60% has to be here. So these two things have to. So sometimes you can do something. So these two things have to add. So let's put little a and b here, little numbers. So 0.15 plus 0.05. I won't write it up here because it will be hard to trace later. Those two things have to add up to the 0.20 a plus b, a plus b plus 0.15 plus 0.05. That's the 60% out there. I think I need one more piece of information to divide this up. Let's say that the chance of an iPod, if this one would say 10%, just switch colors. This is 10%. Here, then that's 20, 30, so there has to be 30% out here based on that. So I think I need one more piece of information to get it all worked out that I wrote down initially. Right, so but anyway, it's once you get, so all of these things should add up to 1, right? So 30, 40, 50, 60, 70, 80, 90, 100, oh, that's too much, isn't it? All of this adds up to 30. Maybe that's too big in here. What if this is, what do we have here? So 20, 30, 40, 50, 60, 65. So these things, these two together have to add up to 35, don't they? So 40, 50, this has to be, the probability of the computer has to be 55. So I think I set something up that didn't quite work. So this is 35, 55, maybe this is 0 in there. So 55% for the computer, 0 is there, 40, 50, 60, 70, 80. That adds up to 1. So anyway, that wasn't the swiftest thing, but you get the idea that you have to read the context and figure out what part is it. And although this is a Venn diagram, it might seem just like a more elaborate example of a simple concept. Often in probability, you're thinking about the opposites of things, trying to reason out what are disjoint events, what really is separate from other things to answer questions, right, of one sort or another. But any questions about those types of things? So I'll show you one more thing before we break, because we have just the time, is that, so on the homework is first describe some probability, some topic, some area, or something you see in the news or somewhere that seems interesting, that's connected to probability, and just write a couple sentences about it. Some of the problems have you do some division of probabilities based on Venn diagrams, set rules, in a couple of contexts to get practice in dividing those up. What we'll do on Thursday is more of the stuff about counting. Right, events are equally likely under different scenarios. How many outcomes correspond to the event that we're interested in, and we can get a probability. So to do those things, we look at ways of counting the number of possible ways things can happen. and we'll do that part on sampling, on counting there. But another source that's sometimes used for probabilities are tables, right, or big surveys. So if you're thinking about randomly picking people, you know, from a population, and a certain percent of the people in the population have a characteristic, right, then the chance that you pick somebody with that characteristic, assuming everybody has an equally likely chance to be picked, would be a table. And so this is a table from the US Census Bureau about poverty. They have ones about unemployment and having households and many other things. But this is based on estimates from different current CPS in there is the current population survey. Again, this is based on interviewing 72,000 households every month, and they use data from multiple months kind of combined in a very complex way. But they come up with these estimates. This is for all races, by age and a few other factors. You know, all people in families, people in unrelated families living together, unrelated individuals living together. So at all income levels, there are a total of 322,549 thousands of people. Right? This is 322 million people living in the United States. There's a definition of poverty based on the size of their family, about their household and all the income sources coming in. And so 39,698 thousands, or almost 40 million people, are classified as living in poverty. Right? So that's a percentage of 12.3%. Right? So 12.3% of people in the United States are classified as live at the poverty line or below. Right? So if you randomly pick somebody, and for your study, the chance that you would find somebody in poverty according to the official definitions would be 12.3%. Right? And one thing that we will do in probability is look at how probabilities change as we make things more specific, as we condition or make it dependent on other information. Right? So people in families, the rate is 10.3%. People in other circumstances that are not living in families or overall had higher poverty rates. Right? For people that are under the age of 18, poverty is higher. Right? So poverty rates are higher for children than they are for adults. Right? You can divide it by males. The poverty rate for males is 11%, but the poverty rate for females is 13.6%. So there's a difference there. And so sometimes, based on big numbers of the population, you can think about randomly picking people, and then the rate in the population translates into one of these populations. When I think about uses of probability, I think about important questions like differential rates of poverty and things like that. If you go to other tables that are in there, they also have this for different racial groups. So this is white alone as that one of the tables, white non-Hispanic. Again, in the current population survey, race ethnicity is self-report. So it's people classifying themselves according to different categories. Right? And so it would be lower than the average there. That implies that it's going to be higher for some other race ethnicity groups. Right? And so this table was black alone. Of course, there's many different ways to characterize different race ethnicity groups. This is the current one as it's reported on this table. Again, it's a self-report question where people can check many different categories of race, ethnicity, black, African American, for example. And the poverty rate is higher. This is how we know, besides anecdotal evidence, that there's inequality by estimating these probabilities from surveys and this. And I didn't select all the tables. with Hispanic, also had a higher rate of poverty. And so we'll use tables like this for counts for thinking about the chances of different individuals in some ways. So sometimes we do abstract things about college students and imaginary surveys and the technology they have in there. And sometimes we'll do things with actual large-scale data sources and estimates that contain the more important questions. Right, if you have those information forms, you can just bring them up here. I'll collect them as we go, and I'll see you on Thursday.
You were right.
Great.
Like
Okay.
being gone the last week classes.
Okay.
For Switzerland.
Yeah.
So it looks like I'll miss
Thank you.
probably 3 classes in the end projects. Would it be possible to just turn the homework early?
Yeah, so the project will be announced early enough. We can work on it before then.
Okay.
And it can be back to the final. So I think that's still,
Typically have,
that would still be okay with me.
typically have 3 hours of class.
Thank you.
Just try to get everything
2 times
available, so you're trying to do it a little bit ahead of time.
Awesome.
Okay.
All right, thank you.
Thank you.
Still hours in class twice a week though.
Really? I guess maybe they're assuming like no homework thing.
Thank you.
Oh, I guess.
Oh, by the way.
Yeah. Figure out where to go.
Great. Thank you. Yeah.
Yeah, let me know if you come to get another session.
Yep. Thank you.
Thank you.
All right, come on in. I'm just finishing up.